Yeah. The topic that I want to talk about here is the potential privacy concern in AR/VR devices. And this work is based on the paper. The paper title is Face Mic, inferring live speech and speaker identity via subtle facial dynamics captured by AR/VR motion sensors. And my name is Tianfang Zhang, and currently I'm a second-year PhD student in WINLAB, directed by Professor Ying Chen. And this is a collaborated work with Shanghai Jiao Tong University in China and also Texas A&M University and University of Tennessee, Knoxville. And this paper has been published in Mobicom 2021, which is a top-tier conference on mobile computing area. And currently, augmented reality and also the virtual reality, which is called AR and VR, these devices have attracted millions of users, and currently such a rapid expansion facilitates a broad array of emerging AR/VR applications, such as AR/VR gaming. This example is a very famous AR/VR gaming applications, Cyberbeat, and also the AR/VR shopping. We can perform like we are shopping in a real shop in AR/VR applications, and also the AR/VR banking and healthcare services. And also lots of people use AR/VR applications for educational purposes. And the control logic of AR/VR devices has been largely shifting towards headset-dominated interaction via the voice interfaces from the controller-dominated interaction. In headset-dominated interaction, we use the voice commands to control the AR/VR applications and the operations. And for the controller-dominated interaction, we use the controller to control where we click and which scene we want to look at using the controllers. Just click the buttons in the virtual environment. And this will cause speech-induced facial vibrations when the users are using voice interfaces. Because the AR/VR headset, they are closely mounted on the user's face during the practical usage, and thus it can capture facial vibrations induced by human speech. And in this work, we have explored the built-in zero-permission AR/VR motion sensors to explore the possibility of capturing such speech-induced facial vibrations. And why we are using zero-permission AR/VR motion sensors here? Because the AR/VR motion sensors, they have played an important role in the AR/VR environments, because they help the users to track the motions when they are using the AR/VR headset, and they also play an important role on creating virtual environments and also the virtual coordination computation. Yeah, and the facial vibration, they will cause some potential privacy leakage, which is related to human's identity and also the human's gender information. It will cause the leakage of the wearer's identity. When the user is watching or doing some shopping, they will expose the facial vibration. They will expose some watching and shopping preference of the user. And when the user is using some applications such as AR/VR traveling applications, these vibrations will also expose AR/VR travel histories and also the user's application usage habits, which application they are using. And also they will expose gender informations, such as the adversaries will use these gender informations to push out advertisement, which is related to the user's gender information. And they will also analyze the gender-specific behaviors based on these facial vibrations. And there are also some other privacy leakage, which is related to the sensitive speech content. It will expose a broad array of sensitive information in the speech content, such as some important numbers, such as social security numbers, the phone numbers, the passwords, and the transaction histories, and also some healthcare informations. And we have explored two different types of facial dynamics in our work. The first is the facial muscle movement. It is the dynamics of facial muscles during the speech, because when the users are speaking, the face muscle will move correspondingly, and it will reflect speech content and also the facial biometrics, such as facial structure and facial fat percentage, something like that. And the second type of facial dynamics is a bone-borne vibration. It is a conductive vibration produced by the vocal cords. During the usage of the AR/VR headset, users speak, and then the speech will conduct through the vocal cord, then to the facial bones, and then conducted to the AR/VR headsets, to the motion sensors of the AR/VR headsets. And we have explored the features of responses of the AR/VR motion sensors. We have do some preliminary experiments to capture these two types of facial vibrations using the AR/VR motion sensors. We have accelerometer and a gyroscope, these two types of AR/VR motion sensors. They can pick up facial vibrations through the headset. And we ask users to speak some specific words, and we can explore that facial muscle movement. It will influence low frequency sensor readings because they are facial movements. They are distributed in low frequency bands. And for the bone-borne vibration, they will impact the high frequency readings because they are vibrations. They are distributed in high frequency bands. And this is the threat model of our proposed attack of FaceMac. For the adversary's capability and the attack procedure, the adversary will deploy a malicious application which is installed on the victim's AR/VR devices. The adversary will first post this malicious application on the application stores of AR/VR devices, and then the victim will maybe they will download such applications, and this application will collect the motion sensors data in the backend, and then store it, and then send it to the adversary for further analysis. And then the adversary use this motion sensor data, use learning-based methods to derive the victim's gender, identity, and speech content, the privacy-related information. And we have summarized the different types of attack scenarios and based on the different training requirements. The scenario one is an attack with prior victim's data. This is like the easiest way, the easiest attack. The adversary will have access on the victim's labeled data ahead of time, and they will record audio data remotely during the AR/VR voice chat. And the scenario two, it is like a more complicated attack scenario compared to scenario one. It is the adaptive training during the attack phase. The adversary will have a pre-trained model built on the other people's data, and they will utilize the motion sensor data collected in the backend in the attack phase to update the pre-trained model through the unsupervised adaptation schemes. And the third scenario, it is more like a real-time attack without prior victim's data. It is more close to the practical scenario. And this is the most challenging attack scenario compared to scenario one and also scenario two. The adversary will directly use a pre-trained model built on other people's data collected by the adversary. And for the signal processing, the adversaries first need to do like speech detection and also segmentation. They will leverage high frequency bone-borne vibration as a standard to detect the speech. And bone-borne vibration only present during the speech pronunciation. And they are resilient to body movements because they are distributed in relatively high frequency bands. And we compute, the adversaries can compute accelerometer spectrograms of the 3 axis over 100 Hertz and leverage as a threshold-based methods for the segmentation. And we can see from the spectrograms here, we can accurately locate the segmentation that includes human speech. And we also need to do body motion artifact removal because during the interaction, with between the users and also the AR/VR headsets. The users may like perform different kinds of body motion to interact with the AR/VR headset. And here we design we design a deep regression method because we find that simple high-pass filter will not work because it is more like unpredictable. The body motion is like more unpredictable compared to like compared to like simple signals. And we use a deep regression model trained with a sensor spectrogram of the speech and the sensor spectrogram data mixed with the motion artifacts, try to build up a mapping between the signal with the body motion and without the body motion. Build a deep regression model to remove the body fat, the body artifact. And after this pre-processing, we and after this pre-processing, we extract features from the facial vibration signals, from the like fine-grained facial vibration signals. For the first type of the facial dynamics, the facial muscle movement, we calculate the 3D speed and also the displacement through numeric integration and extract time and frequency domain features from the 3D acceleration, speed, and also the displacement. And for the bone-borne vibration, the second type of the facial dynamic, we use spectrogram to capture this bone-borne vibration and to represent the features. And we can see that from the two figures, from the speed of the word one and the displacement of the word one, we can observe that the pattern is quite similar, but the direction and the other like the direction of these patterns are different because they are two different users. They may have some like same features, and they also have features related to the user itself. And then for the tasks, we do gender and speaker identification. First, we implement a representation extractor based on our previous feature extractions. We design two CNN-based models to derive the representations from the vibration features. And also we design a gender classifier and also speaker classifier to make classification on the gender and the speaker labels. And we detect the speaker and the gender label based on the derived representation. And these representations can also be used to obtain the speaker's identity. And another more harder task is a speech recognition. We want to classify the speech content from the facial vibrations. It is a more like challenging task because the speakers, they have some like speaker dependent characteristics. And to solve this concern, we apply an unsupervised domain adaptation scheme on the motion sensor data, which is collected during the attack if the label data is not available. We implement this module because we want to remove the artifact, the impact of different speakers. And this is the whole diagram of our proposed attack of the face mic. We have data pre-processing. We make segmentation. We remove the body motion artifact. We extract the features from two types of facial dynamics from the facial muscle movement and also the bone-borne vibration. And we design deep learning-based sensitive information derivation network. We have gender classification and identity classification and also speech classification. We involve adaptive training to remove the artifact of different speakers for the speech classification. And for the experimental setup, we have do comprehensive experiments on 4 different kinds of mainstream headsets. First, Oculus Quest, which is also known as Meta Quest, and the sampling rate of the motion sensor is 1 kilohertz. And also HTC Vive Pro, another types of commodity AR headset, and also the Google Cardboard with different types of smartphones. And for the speech content, we involve 11 different digits, and from 0 to 9. And for the word, for the speech content classification, we involve 20 different pretty good privacy words, which is a public data set in the community. And for the participants and data collection, we collect the data from 45 different participants with a sound pressure level of 67 dB to 73 dB, which is in the range of the normal speech volume. And we test our attack in 6 different environments across 3 different universities. And for the speaker identification task, we can achieve over 97 and 93 success rates on the MetaQuest and also on HTC Vive Pro, respectively, 2 types of standalone headset. And we can also achieve over 94% success rate for cardboard, the low-end smartphone-based VR headsets. The results show that show the effectiveness of our proposed attack on speaker identification task. And for the gender detection, we involve 3 different aforementioned 3 different scenarios: attack with prior victims' data, adaptive training during the attack phase, and the more challenging real-time attack without any prior victims' data. From the results, we can see that we can achieve over 99% success rate under scenario 1, under the easiest scenario. And we can also achieve more than 85% success rate for scenario 2 and also scenario 3, more close to critical scenario. And we do not involve victims' prior data for training in these 2 scenarios. And for the speech recognition task, more challenging task, in scenario 1, we can achieve very high success rate. We can achieve 99% on MetaQuest and also on HTC Vive Pro, and 93% for the 2 kinds of low-cost smartphone-based cardboard headsets. And for the more challenging scenario 2 and scenario 3, we can also achieve more than, for the scenario 2, we can achieve more than 48% accuracy on the top 1 success rate for the digit recognition and also for the word recognition. And for most challenging part, the scenario 3, we can also achieve 40% accuracy on the top 1 success rate for digit and also for word recognition. Yeah, let's sum up our work in several paragraphs. Yeah, we propose the first attack, which is called face mic, that infers private and sensitive information using the facial vibrations associated with live human speech while using the face-mounted AR/VR devices. And we also find that the speech effects in the motion sensor readings are dominated by the facial muscle movements and the boom-boom vibrations. These 2 types of facial dynamics when the users are using voice commands to control the VR/AR headsets. And we design a series of techniques to infer the headset's wearer's gender, identity, and a simple speech, this sensitive information. We have segmentation methods. We have body motion artifact removement. We have lots of feature extraction modules. And we demonstrate that face mic can derive the headset's wearer's sensitive information. With 4 mainstream AR/VR headsets, we have included 2 types of standalone AR/VR headsets, the MetaQuest and HTC Vive Pro, and also 2 low-end smartphone-based cardboard devices. Yeah, thank you. That's it for the presentation. And I'm happy to answer the questions and hear the advice from the audience. Yeah.
Thank you, Tianfang.
Yeah.
Have you thought about any countermeasures that could be effective?
Yeah, actually, I have. When we were doing this work, we have thought about the countermeasures. Because we cannot delete the motion sensors because they are playing important role on creating 3D virtual environments. I think the possible solutions that we can do is that we can encrypt or try to use hash method or something like that, right, to encrypt this motion sensor readings. But the system can use the original values of the motion sensor readings, but they cannot be used by the adversaries. Maybe we can also like set a limit on the sampling rate of the motion sensors, because for like healthcare applications and also like motion tracking applications or something like that, they only need like maybe like 20 hertz or 40 hertz, this level of sampling rate. They can successfully achieve their basic functions. Yeah, but for the commodity device such as MetaQuest and HTC Vive Pro, we can raise up the sampling rate to like 1 kilohertz.
Right.
That is unnecessary, actually.
And is that necessary for your attack? To have such a high frequency?
This is like necessary for the attack, but it is not necessary for
application.
Yes, yes, exactly.
And that's a good countermeasure.
Yeah.
Okay. All right,
Thank you.
Thank you.